Hello and welcome to the MOOC on optical communications. In this module we will talk about detecting light, which of course forms the major component of an optical communication system, because you would have taken the electrical signal which would be representing some information, and you would have used an optical transmitter to convert this electrical signal into an optical signal, and this optical signal would have travelled from the transmitter side through the optical fiber. There might be additional WDM components through which this optical signal would have passed through, but as long as it remains optical, you cannot extract the information back unless you convert this optical signal into an electrical signal, from which you will perform the extraction of the information. So, the objective of the receiver, the first task of the receiver would be to extract the electrical signal from the optical signal. Okay. So, how do we perform this function of converting the optical energy into electrical energy is the subject of detecting light. So, when we say detection of light, what we mean is conversion of the optical energy which presumably carries some information onto the electrical signal. So, we of course have chosen it to electrical signal. You can in principle choose it to convert to any other energy, but we know that we have been working with electrical signals. So, our objective would be to convert optical energy to electrical energy only, and any such conversion transducer can be thought of as a photodetector. Okay. Photodetectors simply mean that they will convert the optical energy into a suitable energy. In our case, this suitable energy form will be electrical. If for example you choose to convert this into a thermal energy, then this can be done by what are called as thermal photodetectors. They will work by the principle of absorbing light in the form of photons, right. So, light consists of photons in the quantum sense. So, it will absorb these photons and then convert this absorbed photon energy, because once you absorb photons you are gaining some energy, and this energy will be converted into the heat energy of a particular material. Okay. This heat energy of course can further be converted into an electrical energy, right, by putting up a digital thermometer, in the sense that you can perform a digital detection of the thermal energy and then use that for extracting the information. These thermal detectors have a very wide bandwidth. Unfortunately, they suffer from extremely low sensitivity, that is to say they cannot detect optical signals which are low in power. Okay, because they require substantial amount of optical energy in order to convert that into the thermal energy. These are not the ones that are preferred for optical communication system. So, what exactly do we use, what kind of detectors do we use in optical communication system? Well, these are all the semiconductor diodes. Okay. So, a simple diode such as a PN junction, when you reverse bias a PN junction, you know that from your electronics courses that there will be a depletion layer which is formed between the P and the N type junctions, and the amount or the width of this depletion layer is controlled by the reverse bias that you are going to apply. So, once there is a depletion layer which mainly consists of immobile ions, right, which causes an electric field between them. If there is a photon which falls on this depletion layer, then it can create an electron hole pair. Okay. So, this photon which falls on the depletion area, that photon can be absorbed by the semiconductor material and then in turn convert that absorbed photon into a electron hole pair, which are then drifted apart in opposite directions because of the inbuilt electric field which the depletion layer provides. This is the fundamental way in which semiconductor materials are used for photo detection, and we will look at couple of those photodiodes. Okay. Now, most commonly used PIN photodiodes and the more sensitive APD photodiodes. APD itself is avalanche photodiodes, so we might simply call them as APDs. Okay. So, before we begin, let us actually look at what makes a good detector. I mean, if I have to use a detector for a 10 Gbps communication system versus 100 Gbps communication system, there has to be certain characteristics of these photodetectors that are important to me, right. So, one would obviously be, if I have to increase the bit rate, I know from my system design part 1 that there is something called as a rise time associated with the photodetector, right. It is essentially the response of the photodiode to a step optical input. Okay, so if there is a sudden change in the optical power, will my electric signal in the form of a current be able to track this sudden change, or how slowly it changes over its state is determined by the response time of the photodiode. So if I want to send signals at a much faster rate, increase the bit rate, then I have to minimize this rise time of the photodiode, right. So one of the important things that I am looking for in a photodiode circuit is how fast it can respond to the optical changes, optical power changes, how fast it can respond. Such a characteristic is related to the bandwidth of the photodiode. The larger the bandwidth, the faster will be the photodiodes. So fast response is perhaps the first and foremost important criteria for optical communication based photodiodes. I mean, in some cases where you do not require this fast response, well, you can use different materials, but in optical communication systems, especially at very high bit rates, we require a fast response from the photodiode. So if everything else we have taken care of, maybe we have minimized the rise time of the transmitter, we have chosen excellent fiber with almost zero dispersion, right, and therefore minimize the fiber rise time. But then if we use a very bad photodetector, which is a very slow photodetector, then all the advantages that we have gained by optimizing the transmitter and the fiber is gone. So in order to avoid this, I need to use a photodiode which is fast enough. So it can respond to very high bit rate, very high bit rates. It can support very high bit rates in the form of changing optical powers, right. So very quickly it has to track the changes in the optical power. So that is one of the major characteristics that you are looking for when you are buying a photodetector or you are designing a photodetector circuit for optical communication system. The second characteristic that you are interested is to say what would be the sensitivity of the photodiode. By sensitivity we mean that what is the optical input power, minimum optical input power that is necessary in order to cause a certain current in the photodiode. Okay. So if my photodiodes, if I have a choice between two photodiodes, one whose minimum optical power requirement is minus 30 dBm, that is 1 microwatt, or the other one which can go down and measure up to minus 60 dBm, which is 1 nanowatt. Clearly the second photodetector, which has minus 60 dBm sensitivity, will be preferred over the first one. Of course, there are certain trade-offs that you have to take care of. If you lower the sensitivity too much, then any instabilities, any small changes in the optical power can be amplified or can be essentially detected as a signal. So there are some problems associated by making the sensitivity too low, something that we will talk about it when the situation arises. Okay. For our current module, as a use of photodetectors as a in functional block of optical receivers, fast response as well as sensitivity are the two most important criteria. Okay. So sensitivity is associated with a high current gain. As we said, photodetectors work by absorbing optical energy in the form of photons and then convert that into electrical signals in the form of a current. So you want a low optical power as the input, okay, but at the same time you want that low optical power to be converted into a very large amount of current. So you want a very high current gain for your photodetector, and that of course is one of the side characteristic which is the result of having the sensitivity along with you. So these are essentially two main characteristics that you are looking for from the signal perspective. Now it is not just that a photodetector circuit simply converts the optical energy into electrical energy. It does so. While it does this conversion, it will also add a certain amount of noise. Noise is a very important topic for photodiodes, photodiode circuits or photodetector circuits, because noise comes from the way you package a photodiode, the way you put the leads for your wires to take out the electrical current, the load resistor which you are using, what is the photodetector connected to, what is the next stage of the amplifier that is connected to the photodiode. All these things matter. Okay. Every component out here will give enough amount of noise. So one of the characteristics that you want from a photodiode is that it must add very little amount of noise. Okay. So low noise is one of the important criteria from the noise perspective, because if my photodetector adds very low amount of noise, then I will be able to take the signal, optical signal at very low powers, yet I have sufficient signal to noise ratio at the output in order for me to detect information sitting in my desired signal. Okay. So, it has to be low noise, and this low noise condition coupled with sensitivity, that is the sensitivity is the lower optical power. So, coupled with these two is a very important trade off that you have to take care when you are designing a photodetector circuit. What we normally do in order to improve the response of the photodetector is that we use what is called as metal semiconductor. There are many techniques, these are the most common ones. So, you use a metal semiconductor metal junctions. We know that metals have a large conductivity, right. So, if the semiconductor absorbs photons and converts them into electrons, then if you put a metal, then these electrons can quickly jump over to the metal side and then constitute a nice current. So, you get a high gain, current gain, as well as the response basically becomes very fast, because an electron traveling through a semiconductor device will have a slower velocity compared to this same electron traveling through a metal because of the abundance of these electrons. So, it actually improves the response. So, these are called as MSM photodetectors. So, this basically improves both bandwidth as well as the current gain. So, it has both high bandwidth as well as high current gain, or large bandwidth and large current gain. The other technique that we normally use is what is called as, this is even more common than the first one, is what is called as separate absorption and multiplication detectors. Okay. This principle is very interesting. It simply says that you first have a separate layer for absorbing optical power. So, optical power, when it falls on the photodetector, there is a region which simply absorbs, okay, and generates what are called as primary electron hole pairs or primary photocarriers. These primary carriers will then go and be collected into another region called as multiplication region. In this multiplication region, each of the primary electron hole pair which is collected there will bombard with the existing lattice in order to generate even more electron hole pairs. So, there is some sort of a secondary electrons which are being generated as a result of the primary electron hole pairs which have come from the optical input. Okay. So, the second region wherein this ionization is happening, the many more electron hole pairs are generated by the impact ionization, which can quickly lead to what is called as avalanche effect, and hence very large currents, okay, flowing through the photodiode, is a very important characteristic for low sensitivity optical detection. So, if your detector has to work at say minus 110 dBm, you can imagine how small that optical power is, you want to use this characteristic. In a more general sense, this characteristic is called as a photomultiplier, and photomultipliers are also used in the visible range of optical communication. So, in the visible range when you are using, then you use photomultipliers, but when it comes to optical fiber communications where the frequencies are in the infrared, mid infrared, you will be using these photodetectors, okay, semiconductor photodetectors. The commonly used SAM photodetectors, the separate absorption multiplication photodetectors, are made out of indium gallium arsenide and indium phosphate heterostructures. Okay. Hetero means different, structures are essentially the layers of photodetector circuit. Okay. The characteristics of indium gallium arsenide is different from the characteristic of indium phosphate, and these two are sandwiched. The indium gallium arsenide is sandwiched between indium phosphate layers. Okay. So, this is called as a heterostructure, and these are the ones which are commonly used for photodetection. Now, this was just probably a very simple introduction to photodetectors. We have not put down the metrics of a photodetector, right. So, I have a photodetector or a photodiode. Okay. From an external black box point of view, I will apply some optical input power to this. Okay. So, we apply an optical input power to this, then what I get at the output is a photocurrent IPH. Okay. There is something called as quantum efficiency, and this quantum efficiency is denoted by eta, and I have used another subscript E just to denote this as the external quantity. External means that I have designed my photodiode, I do not have access to the internal working of the photodiode. Someone has given me a photodiode, I am just using that one in my circuit. All I am interested is to see what would be the fraction of the optical power that is absorbed by the photodiode and converted into electron hole pairs. Please remember that this particular metric is used commonly for the PIN photodiodes, that is because there is no secondary electron hole pair generation. Okay. So, this is the primary electron hole pairs in the PIN detectors, therefore, this external quantum efficiency is what we normally use. Okay. This external quantum efficiency tells you the number of electron hole pairs that are generated. Okay. These are generated because of absorbing the optical power. Let us consider a typical photodiode. Okay. So, let us say this is my photodiode which has a thickness of d, because one of the things that I have to first ensure is that if I am generating these electron hole pairs due to absorbing optical power, right, the optical input power is P opt. So, if I am absorbing the optical power, I need to know how much I am actually able to absorb. I mean, what determines how much do I absorb? If I am a photodetector and I am bombarded with certain photons, there has to be certain characteristic that has to be there within me in order to absorb these photons, right. It turns out that at the simple level it is dependent, absorption is dependent on two quantities. One is called as the absorption coefficient of the material. Okay. This absorption coefficient is typically a quantity that is measured as 1 over centimeter. Okay. So, if I take a thickness of certain centimeter d centimeter, then I know that the power absorbed will be given by, will be dependent on alpha and d. Okay. In fact, you can find out that if at the input you are coming in with a certain power, optical power P at 0, the power that you get at the output will be, after absorption. So, if some power is absorbed inside and some power of course not absorbed will come out as the residual power. The residual power will be equal to whatever the input power that we have supplied to the photodetector times e power minus alpha d. This is the attenuation thing that we have seen in our earlier modules for optical communication. Now, if this is the power that is coming out, what would be the power absorbed over the section length d? The power absorbed will be whatever the input power minus power that is coming out, right. So, this much of the power has been absorbed inside. So, this is, if you take this P of 0 as a common factor, so you get e power minus alpha d. A quick question to all of you before we go ahead. What should I do in order to make the absorbed power to be almost equal to P of 0? A moment's reflection will tell you that I have to make this term go to 0, right. So, when will this e power minus alpha d term go to 0? When alpha d is much larger than 1, okay, or d is much larger than 1 by alpha. We call this 1 by alpha as the attenuation length, okay, or the absorption length, let us call this as LA. So, what we have to ensure is that my photodetector thickness is much larger or longer than the absorption length of the material that I am using. Now, here is an interesting thing. We know that if I make the detector very long, right, the thickness of the detector long, then the electron hole pairs that are generated must travel towards the end or towards the edge of the region of absorption in order to be collected by the other regions in order to form the current, right. So, my circuit will be connected to the photodetector. If the photodetector itself is of this length, then any electron hole pairs that are originating at the junction where the light is being supplied will have to travel all the way here, right. So, they will have to travel all the way over here, or anything that is say maybe originating at the middle, electron has to travel here, the hole has to travel here in this way, whatever the way in which we have connected the circuit. But the point is that they have to travel this length. Worst case scenario, edge generated photocarriers have to travel all the way through the absorption layer, right. So, if I make this larger, yes, I am able to absorb my optical power, in a better way, but long transition times, right. I start here and then I have to travel all the way to the edge. The transition time, which will be in some sense inversely proportional to the speed of the photodiode, will become large. The transition time will become large, the speed or the response of the photodetector suffers. So, here is our first and main problem. I want to absorb as much as power, but I cannot do that by simply increasing the thickness of the photodiode, right. So, there is actually a trade off between how quickly you want to measure signals versus what would be the quantum efficiency. Okay. In addition to this, the second thing that you might be interested is, as from the external black box point of view, you have generated some electron hole pairs, okay, which you probably do not have an access to, right. These electron hole pairs have to be converted to electrons in order to form a current, or holes in order to form a current, right. So, these have to be collected in the appropriate regions and made to go through the external load resistor that you have connected. Okay. So, if you have to do that, you have to know how many of these EHPs are converted to current, right, or converted into electrons, right. We know that although an electron hole pair is generated, it is the electron which actually kind of physically moves, hole moves virtually, right. But whether it is a hole moving virtually or electron moving physically, they both will constitute one charge carrier, right. So, we can actually, instead of saying this as current and electrons, if I send in some optical power which then gets converted into electron hole pairs, which then gets converted into current, because electron hole pairs are the photo generated carriers. So, I should not have distinguished between the two. My point was that electron hole pairs might be generated, but I might not be able to harness all the electron hole pairs. That is, not all the electron hole pairs that are generated because of the photon absorption will contribute to the final current. You might ask why, what will happen to those electron hole pairs? I mean, they have been generated in the depletion layer. So, what is the problem in converting that electron hole pairs into actual current? Well, they are generated, but while they are drifting towards the region, they might actually recombine. Okay. Sometimes they might be generated and quickly recombine before they have had a chance to go around the circuit. So, because of these losses, right, and moreover as the electron is travelling, it might be lost because of the absorption itself. So, because of all these factors, you do not always are able to convert electron hole pairs into 100% into a current. Okay. So, this quantity again externally one can measure by looking at how much optical power we provide as input versus what is the photo current that is generated. Okay. This is effectively what I can measure. So, I can take my photodetector, bias it, apply an optical power, and then look at what is the current, right. We were looking at the number of electron hole pairs that can be gainfully converted into the current, right. So, we send in a certain optical input power P opt, and then you are looking at what would be the current that is generated. Okay. Now, what we are interested is to see how much of this electron hole pairs are converted into current, but what is the number of electron hole pairs that are generated, that depends on the efficiency of the photodiode, right. So, if I send in this many number of photons, because optical power divided by HF will give me the number of photons, right. So, this number of photons multiplied by eta, which is the efficiency, I am not denoting this by eta E, I am assuming that this is just the efficiency which we have defined, we do not have to specify it as external and internal for this particular case. So, eta is the efficiency of the photodiode times P opt by HF gives you the number of photons. So, this effectively tells you the actual number of photons, and these are the number of photons which are generating, the actual number of photons which are generating the electron hole pairs. Okay. This electron hole pairs, each of them will carry a charge of Q. So, the amount of carriers that are generated, right, is given by this particular quantity into Q. Okay. We assume, of course, in this particular case that all these electron hole pairs have been able to generate one charge of current. Okay. This number will be slightly smaller than 1. One can define one more efficiency factor over here, but you can also put all those efficiencies into the same eta. That is where the concept of an internal quantum efficiency comes in. Okay. So, if we do not want to distinguish all that, we can simply say that eta will be the fraction which tells us what would be the optical power to the actual amount of photo carriers that are generated. Okay. This would be the amount of the current that we actually measure on the output circuit, right. This is the current that we are measuring, and this photo current to the optical power is called as the responsivity of the photodiode. So, responsivity is something measured is a quantity that is measured in ampere per watt being the optical input power. So, it is what would be the current in ampere generated to what optical input power we applied, and this quantity is given by, so you can put this P opt in this equation to the denominator, and then you see that this is given by Q eta divided by H into F. Okay. So, you can further simplify this expression by calling this Q, writing down the value of Q, which would be about 1.6 into 10 to the power minus 19 coulomb, right, and H is 6.634 something into 10 to the power minus 34. I am just remembering the order of the magnitude over here, and then you also have frequency. If you express this in terahertz, which is the frequency of the optical photons which are used for optical communication. So, these are the terahertz in region, hundreds of terahertz of course. So, this if you put in, you can simplify this equation to eliminate all this big order of numbers. Okay. Let us not do that one here, I will give this as a simple exercise for you to do that. So, to summarize what we have been talking about, we want a fast photodiode, okay, which has a low sensitivity, that is can detect the very small optical powers. Okay. So, it can detect optical powers which are very small. A low optical power, you want a large responsivity. Okay. Again, this responsivity is for the PIN detectors. Okay. For an APD detector, you have to multiply this one by a certain factor. We will talk about it in the next module. For the PIN detectors, the responsivity is measured in ampere per watt, and remember, PIN detectors will only generate primary electron hole pairs. There is no multiplication of the electron hole pairs involved there. So, you want a very large responsivity, which means that there is a large current gain. You also want a very high quantum efficiency, so that you can actually absorb as many photons as possible. So, with this basic idea of a photodiode, we will stop in this module. In the next module, we will actually consider the materials that are used and talk about the two structures of the photodiode. Thank you very much.